MooMooMath. Today we are going to look at converting coordinates between polar and rectangular forms. So you guys already know from vectors these two rules, that the x-coordinate in a vector is equal to the r times cosine theta, where r is your magnitude and your x direction is cosine theta, and the y-coordinate is r, or the magnitude, times sine theta. And we looked at it like this: the magnitude times, whoops, that's supposed to be magnitude, times cosine theta and sine theta. So all we're doing is we're looking at taking that magnitude, which is the length, and distributing that in. Well, that's the coordinate on the polar system, the x and the y direction. You guys also know these two formulas. You know that tangent theta is y over x, because we know defined that tangent is opposite over adjacent. And we also have the equation of a circle. So r squared is equal to x squared plus y squared. That's just representing the hypotenuse of a right triangle also. So how does all this work? How do they all connect? Well, I'm going to show you real quick. We're going to take the point 5 and pi fourths for a second, and we're going to graph that with polar coordinates. So I'm going to go over to 1, 2, 3, 4, 5, and I'm going to rotate to pi fourths. So that's that position as a polar coordinate. Now I'm going to show you how it works with a rectangular coordinate. We know that we have this direction and this direction, which is an x direction and a y direction. Now, we know the distance, or the hypotenuse, of this right triangle is 5, because that's the length, that's the circle we're on in the polar system. So we need to find the x and the y direction, where it's very simple. We can take that radius, just like we learned with vectors, and we can take the cosine of the angle, which is pi fourths, and the sine of the angle, which is still an angle of pi fourths, and we can distribute the 5 in to get that exact position. So that's just going to be 5 times root 2 over 2, and then 5 times root 2 over 2, and that is the rectangular coordinate, which is your x and your y direction, which we did with vectors. So that's how you're going to end up converting. So let's try a couple of these. So I want you to write down these two formulas. If you're starting with a polar coordinate and you want to work to a rectangular coordinate, to find x, you're just going to take the radius times cosine theta, and that's going to give you the x coordinate in a rectangular form. The y coordinate you're going to simply get by multiplying r, or the radius, times the sine of theta, and that is going to give you the y coordinate. And up till now, that's all you've known. You've only known how to graph in a rectangular form, where you have the point 2, 1, you go to the right 2, whoops, and you go up 1, and bam, there's our position. And that's rectangular graphing. But today we're learning how to graph with polars. Now, what if we have a rectangular coordinate and we want to convert it to a polar coordinate? So we want the answer to be r and theta. Well, to find r, we're going to use the hypotenuse of a right triangle, which is also the radius of a circle. So we're going to use the x coordinate squared plus the y coordinate squared, and that's equal to r squared. So let's just look at this 2, 1. We would take 2 squared plus 1 squared, and we would get r squared is equal to 5. And so the radius would be the square root of 5. Now, this is not related to the last problem, so don't freak out on me. It's not the same as that last problem, but you're going to get the square root of 5. And then we learned how to find rotational angles in the last unit. we just take the tangent of theta, and we take our y-coordinate, which is 1, over our x-coordinate, which is 2, and we use the inverse tangent. So let's grab our calculators, and oops, get my TI up here, and let's look at it, and we'll find out what that angle of rotation is. Now this one's not on the unit circle, and that's fine. It doesn't have to be on the unit circle. So let's take the inverse tangent of 1/2, and we can find out what this rotation is going to be, and it's 26.6 degrees. So I would have 26.6 degrees as my rotational angle. So let's try one of these. Okay, we're starting with a polar coordinate, and we want to move to a rectangular coordinate. So we're going to use the formula to find x. We're going to take r times cosine theta. To find y, we're going to take r times sine theta. So our radius is 2. Our angle is pi. So let's plug in our radius, which is 2, times cosine of pi. Now, let's think about that unit circle. What is the cosine of pi? Well, the cosine of pi is -1. So let's take 2 times -1, and that coordinate is, the x-coordinate is -2. Let's do the same thing to find the y-coordinate. We're going to plug in 2, and we're going to take the sine of pi. Well, we know the sine of pi is 0. So 2 times 0 is just 0. So we now have an x-coordinate and a y-coordinate at -2, 0. And that is our rectangular representation. So I want to now just quickly sketch it so you can see what we're doing. Okay, we have first our polar position. Our polar position is over 2, so 1, 2, rotating to pi. That's here. And then as a rectangular coordinate, I'm going to draw it in green. Our rectangular position is -2, 0, so that's the same position. So you can see if this were like a rectangular with a Cartesian coordinate plane laid on top of it, you can see that those are indeed the same two positions, or the same position written two different ways. So now let's try a second one of those. We're going to start with a radius of pi thirds and a rotation of pi 6. So to find the x-coordinate, we're going to plug in √3, and then we're going to take the cosine of pi 6. So the cosine at pi 6 is positive √3 over 2. And let's multiply that together. √3 times √3 is 3. So 3/2, which is 1.5. That's my x-coordinate. The y-coordinate, we're just going to take the radius, which is √3, and we're going to multiply times the sine of pi 6. Well, the sine of pi 6, we know that to be 1/2. So we're going to have √3 times the vertical direction, which is 1/2, and that's going to give me √3 over 2. So I now have my x and my y coordinates, and I just write it as an ordered pair, 3/2 and then √3 over 2. And there is my rectangular position. Okay, now let's convert the other way. Let's start with a rectangular position and convert to a polar. So we're going to have to find r first. And we know r squared is equal to x squared plus y squared, because we know that that's the hypotenuse of a right triangle. So if we're looking this in rectangular position, we're going to go left -1 and up 1. So as a rectangular position, we're at -1, 1. So we need to know what's this radius. What is the length? Whoops, I didn't draw that very well. Let's erase that and try it again. Let's draw it a little neater. There we go. We need to know what that length is. So I'm going to start with r. So r squared is going to be equal to -1 squared plus +1 squared. So that's just going to be 1 plus 1. So r squared is 2. So r is the square root of 2. And that's going to be the first coordinate in our polar coordinates. So r is the square root of 2, which is just the hypotenuse. Now, we need to find an angle of rotation. So I'm going to take tangent theta is equal to y over x. So we're taking the inverse tangent of -1. Now, this is where it gets a little bit tricky, and we've worked on this quite a bit. So we're going to take the inverse tangent of -1, and that's going to give us a -45 degrees. And yes, it is negative in the rotation because we know inverses, tangents, inverse is going to be in quadrant 4, but we're not in quadrant 4, so you have to think of that as your reference angle, 45 degrees. Well, if you have a reference angle of 45 degrees, we know that rotation is 135, which we write in radians as 3/4. Now, you may have recognized that before we even put it in the calculator. You don't have to use this formula. If you recognize that position from the unit circle, you can just say it's the inverse tangent of -1, and it's the angle's position is 3/4. And that's how you can represent that as a polar coordinate. So we're going to stop there, and we're going to practice a few of those, and then we're going to learn how to convert equations.